Hi, my name's Josh McGrath. I'm the Soil Management Extension Specialist at the University of Kentucky. Today, I'm going to be talking about site-specific nutrient management. So why precision nutrient management? The key here is ecological intensification. And what we mean by that is we're approaching biophysical yield limits or yield plateaus, particularly in the developed world in our cropping systems. That's not the genetic yield potential. We're nowhere near that. But it's the yield potential within our cropping systems with tillage, weather, and everything included. And so as we approach those yield plateaus, we experience a diminishing return function. As this figure shows a diminishing return, we see yield on this top line going up as we approach the economic optimum yield versus the nitrogen rate across the x-axis. We see that the efficiency starts to drop off. This line here, this blue line, is nitrate in the soil down to 1 meter. And we see that right as we approach this optimum level of nitrogen rate and yield is maximizing, all of a sudden nitrogen leaching down into the top meter really starts to increase rapidly in an exponential function. And so the efficiency of nitrogen use drops off exponentially as we approach that optimum yield. And if we fertilize beyond that, we're suffering nitrogen losses. If we fertilize below that, we're suffering yield losses. And so precision agriculture could be a key to achieving ecological intensification. And ecological intensification is when we're managing our inputs most efficiently to match those nutrient inputs in time and space to crop needs to try and increase the efficiency while being at that optimum yield. One of the key concepts when we talk about precision ag and precision nutrient management is accuracy versus precision. And these figures explain it pretty well. If you're a shooter, you kind of understand this concept. So this figure right here shows high precision and low accuracy. You see all the shots are grouped together, but we're not hitting the bullseye. And then if we look at the red figure, we see very low precision but very high accuracy. None of those shots hit the bullseye, but on average, we're dead on in the center of the bullseye. This is how our current nutrient recommendations are built, and they're built that way intentionally. The way we develop a nitrogen recommendation or a phosphorus recommendation is many years, many plots, many different replications with a lot of different nitrogen rates or phosphorus rates, and then we look at yield in each of those plots. And so we're getting an average right rate. And the law of averages, over 10 years, our nutrient recommendations are going to be highly accurate. But every single year and every single spot in that field, you're probably wrong. So when we look at it on a fine spatial or temporal scale, we lack precision in our nutrient recommendations. So let's talk about two fundamental approaches to site-specific management. There's the reactive approach and the predictive approach. In the reactive approach, we're looking at sensor or imagery-based approach that is occurring in real time, and we're reacting to needs expressed by the crop. This is very common in nitrogen management. If we talk about the predictive approach, we create a prescription or an RX before going to the field. It can be based on soil data, yield spatial data like a yield map. It can incorporate other data layers, for example, an EC map where you go out and map the soil with an electroconductivity meter. But this is a very data-intensive approach. It's data-driven, and so junk in, junk out. If you don't have good data going in, the predictive approach isn't going to work for you. And in situations like nitrogen management, where it's very dynamic with time, the reactive approach is going to work better. One of the basics to site-specific nutrient management, and any nutrient management actually, is soil testing. And soil testing is actually 4 separate activities. We've got soil sampling, soil analysis, interpretation of the results, and then the recommendations that come from those results. And all 4 activities make up soil testing. Generally, soil sampling is what we consider the most limiting factor, right? Because results and recommendations are no better than that sample itself. But we've gotten pretty good at characterizing the diversity across the field for precision ag. And soil analysis is very good, very mature technology. The soil labs do a really good job. But we need to answer a few questions about the interpretation and the recommendations for site-specific management or precision ag. These technologies or this area of soil testing is still underdeveloped. When we talk about site-specific nutrient management, characterizing and addressing that variability in the field, you have to answer a few questions. What variability are you trying to address? Are you trying to address spatial variability in yield, trying to bring low-yielding areas up? Are you trying to address variability in soil nutrient concentrations? You've grid sampled the site and you know you have variability in soil phosphorus or potassium and you're trying to bring those low areas up into that optimum range. Other soil chemical properties like liming, pH, soil physical properties, drainage, compaction, those sorts of things. Soil moisture with variable irrigation because you know you have different soil textures in the field. So you have to ask, what caused that variability? We're very good at characterizing the variability, but understanding the causes is most important. And then lastly, how do we address the cause of that variability? What are you going to do to try and address that variability, and what's your ultimate goal? Is it to increase yield or to increase profit? Because these are different objectives and sometimes don't go hand in hand. So as I said before, we're very good at soil sampling and soil analysis, but in site-specific management, the biggest knowledge gap we face is in interpretation of the results and the recommendations to achieve those end goals that we discussed. So the interpretation of soil sample analysis, you get that from your laboratory, whether it's your university laboratory or your private laboratory. And the interpretation of those results is based on regional conditions with representative soils ranging from deficient to adequate for a given nutrient. And then we obtain useful soil test correlation and calibration. And this is key to the interpretation of soil test results. So extractable nutrient values have very little meaning unless they have been shown to be related to that plant response to application of the nutrient or element, and that's correlation, and the soil test level at which that response occurs, which is calibration. And this is that interpretation part that we struggle with in site-specific management. So it's useful to understand soil nutrient recommendations and the interpretation philosophies that go behind them. There's three basic interpretation philosophies that are out there that are most commonly seen. The first is the sufficiency approach. When a soil test level is below the optimum, you apply only enough nutrient to meet crop needs. And then there's a build and maintenance approach. You build that soil test level up to the optimum level, and then you replace nutrients as they're removed. So the difference here is once we're in that optimum soil test zone, we continue to apply nutrients at a crop removal rate. And that's really where the sufficiency approach doesn't do that. And then we have the cation saturation approach. I'm not going to speak much on that. It's based on the belief that there's an ideal ratio of some of the basic cations. And generally, most research has shown, even some of the original researchers that developed this concept, that the cation saturation approach is not scientifically sound. So let's talk about this general concept of soil test interpretation and how it applies to accuracy versus precision and how it might cause some challenges when we talk about site-specific management. So normally we use some sort of hybrid between the sufficiency and the build and maintain approach, but it's fundamentally based on this concept of a below optimum soil test zone, an optimum soil test zone, and above optimum. And in this situation we have this critical level. And the critical level is the point below which on the soil test scale we expect a yield response to a nutrient application. In the optimums area and above optimum, we don't expect a yield response. And there might be an environmental critical level at some point, for example, with phosphorus, where above that soil test level, we may run into some challenge with phosphorus loss and water quality degradation, and we want to be concerned about that as well. But this is the general concept of soil test interpretation. So, how do we place that critical level? Well, it's from field research like this, where we have a lot of yield response across a range of soil test phosphorus. And it really is kind of a cloud of data because different fields and different areas within a field and different years will respond differently to different soil test levels for any nutrient. In this example, I'm using phosphorus. And on the y-axis, we see on the vertical axis a relative yield scale up to 100% so we can compare across fields. And so how do we place that critical level? Well, traditionally we're looking at, you can place it down here close to 30 or up closer to 40, or maybe even as we approach 50 with this cloud of data because there's a lot of scatter. So traditional soil test recommendations that were planned for a flat rate application, we actually place that critical level much higher because the risk of under-fertilizing is much greater than the risk of over-fertilizing economically. So we applied some economical models to this and we looked at probability of response And we put sort of a buffer zone in there, or a slop factor, if you will, to account for the variability within the field, because we know that that critical level may change as we go across the field. The challenge is, in precision ag, we're trying now to be more precise. So while this recommendation system is very accurate, we need to increase its precision if we're going to get true benefit out of precision nutrient management. Again, coming back to this concept of low precision and high accuracy, which is what we currently have, and trying to increase our precision and maybe have high precision and high accuracy. Because site-specific management might not increase yields, because we're at these biophysical limits. We already said that. If we just want to have maximized yields, we can apply a flat rate, a high flat rate across the field, and economically we'll probably still be all right. But if we want to ecologically intensify, then we need to increase the efficiency. And we need to keep in mind this difference between precision and accuracy, and think about how can we manage nutrients to address this spatial variability or even temporal variability.